All right, so today we're going to start off looking at section 5.4, part 2. Okay, we've already looked at 5.4, part 1, okay, which dealt with basic properties of logarithms, okay, how we can combine logs, we can split logs, all that stuff. And we're going to use this to help us solve a problem we did last time. Okay, so we did this problem where we had a population of 50,000 people going up at 2.5%. And the way we solved it to find when the population was going to hit 100,000 was graphically. We graphed 100,000, graphed the population, that's the blue line, and we calculated where it hits 100,000. Right? Now we're going to do basically the exact same thing, except we're going to try it without the calculator. We'll use algebra. Okay, so same problem. Okay, population is 50,000. It's going to go up at 2.5% a year. How long does it take for the population to hit 100,000? All right, so first thing we want to do is just set up our equation we're going to solve. Okay, and that goes back to our exponential growth formula. All right, so it's our population times 1 plus r to the t. Okay, just make sure we change that rate to a decimal. All right, so we'll start with our initial population. Derek, what's my initial population?
50,000.
Yep, start with 50,000 times 1 plus, how about Pat? How would I write my rate?
2.5, right?
Well, is that as a decimal?
No, it's 0.25, right?
Cool, we gotta go one more.
Oh, 0.025.
0.025, so remember, you move that decimal 2 places to the left. Okay, 0.025. Raised to the, Nick, what do I use for my exponent? Yep, it's going to be yearly. So what letter do we usually use for time? T. So we use T. And Amanda, we want to know when this population reaches how much?
50,000. Oh, no.
Starting at 50.
Yeah, 100,000.
When's it going to reach 100? So we already had this equation from what we did back in this problem. Okay. All I'm going to do is combine 1 and 0.025, add them up. So we get 1.025. Okay, that's a good first step. Okay, so 100,000 equals 50,000 times 1.025 to the t. Now, I can't get the t by itself right away, but I can at least get rid of this 50,000. Okay, how would I move this 50,000 to the other side? Yeah, I'd divide, right? Because this is multiplied. If there was a plus sign in here, then we could subtract it. But since this is 50,000 times something, we're going to divide. All right, so let's just divide that out. So we get rid of that. Okay, and on this side, what we'll do is just cross off all the pairs of zeros you have. So get rid of those. So I'm left with 10 divided by 5, which is 2. Okay, so now I just have this equation. Hey, anytime that we have an equation that has a variable as an exponent, we want to change to logs. Okay, so what I'm going to do here, okay, I'd like to be able to move this exponent in front, okay, because that's a rule. We can do that, but we can only do it if we have what function here? What function do we have to have that allows us to move exponents in front? Logs. Okay, if you don't have the word log, you can't just move exponents in front. So what I have to do is take the log of both sides. Okay, so that step's a little tricky if we didn't know that. And I'm going to show you an even faster way you can do this without taking the log of both sides at the start of the next part. All right, so. Okay, now, because I have the word log, what am I allowed to do with that t? I'm going to put it in front. So rather than rewrite it another time, I'm just going to go like that. Okay, and now what would be my last step to get t by itself? Yeah, what would I divide by? Well, the t is okay, right?
Oh, I got
We want to get rid of the thing that's next to the t.
log 1.0.
Divide by log 1.025. Okay, this problem is just like having something like this. It's t times some number. If you want to get rid of the number that's next to t, divide by some number, okay, whatever it is. And then you get t by itself. Okay, I don't care what log 1.025 is, and I'm never going to know. Okay, I don't need to. So that's gone. And there's my answer right there. Okay, I'm just going to type it in and see what I get. Okay, if you remember from the way we did it graphically, I think it was about 28 years. So let's see if we get the same thing. Right, so we get log of 2 divided by, remember log, it's right by the 7, okay, if you're looking for it, 1.025. So we get 28.071. Let's look at what we got graphically. 28.071. Okay, same thing. Any questions on that? And again, there's even a faster way. Not that this took that long, but we can do it even faster in a minute. Okay, and we should put a label on that. That was in years. And they're not going to ask you to round to this many decimals. I'd probably round to 2, 28.07. Hey, questions on that? All right. All right, so next part, we're going to look at how we can fit basically a line or a curve to a bunch of data. And in Algebra 1, you've done stuff like that. Okay, and it was called a line of fit. But in this case, how come a line wouldn't be a good model for that data? Yeah?
It's going up in a slope.
Yeah, because it's curved. Okay, you could try to fit a line to it the best you could, but it really, those points aren't modeled by a line. They would be best modeled by something probably like this, a curve. And what kind of curve does that look like? Yeah, exponential curve. Right, so that's what we're going to look at doing. Okay, we're going to model points using what's called a power function. Okay? Or exponential is another word for it as well. Okay, and a power function is a very simple equation. There's only two things you have to find. You have to find A and you have to find M. Okay, it's kind of like when you have something like this in Algebra 1. Y equals mx plus b. Well, you don't have to find x and y. Those are in the final answer. But what you do have to find is your m, which is your slope, and your b, which is your y-intercept. Same idea here. Similar. Okay, but that's what your final answer is going to look like. Just you're going to have a number for A and a number for M. You got to plug in.
What do A and M stand for?
Oh, like here, M is slope and B is y-intercept?
Yeah, like same thing, or is it?
No.
They just put in there for
Yeah, that's just the letters we use.
Okay.
Since it's a curve, it's not going to have a slope. Okay. Yeah. Or at least it doesn't have a slope.
I didn't know if there's any correlation between it or not.
Yeah, there is kind of a connection between these two. For now, though, I don't think we're going to get into it.
Okay.
It takes a little while to explain, so we won't worry about it.
Okay.
All right. So whenever we're thinking of using a power model for data, okay, first thing we always want to do is make sure that that's the right tool. Okay, power model, you don't use it for everything. You only use it if your data looks like it's curving up. Right, so a trick that we can do to see if a power model is a good fit for our data is they're going to give us a table. We'll take the natural log of everything in that table. Okay, and this is just like a trick. If you do that, and then you look at the new data, if it looks like a straight line, then that means it's a power model. Okay, so it's a trick. I'll show you how it works. So they'll give us a table of data, something like that. We'll take the natural log of every value in this table. Okay? And I'll just write it, right below it or something. And then what I'll do is I'll look at all those new values and I'll graph them. And if they look straight, then I know a power model is probably the right thing to use. Okay, once we determine that we're going to use a power model, then we have to find the two letters I circled on the other page. B. Well, I used A, so I'll change that. We have to find A, and we have to find M. And once we find A and M, then we just write our final answer. Okay, so one time we'll find A and M by hand. The next time we'll find it just on the calculator, and that's how we'll do it after that. Okay, does everybody have those 4 steps? All right, so this problem says determine if a power model is appropriate for this data. And if it is, find the power model. Okay, so here's our table of data. First thing I got to do is check if the power model is the right thing to do. So what I'm going to do, I'm going to take the ln of every number in that table, and I'll just write it down, just put it in a different color. Okay, but I'm going to put it in the same table. All right, so let's start with that. Natural log of 1 gives me 0. Okay, natural log of 3. 1 point, let's just round, let's round to 1 decimal because the accuracy here isn't that important. We'll just say 1.1. Okay, ln of 5. Okay, 1.6. ln of 8. 2.1. Okay, and do the same thing with the ones down below. ln of 5 I already have. ln of 31.2. 3.4. ln 73.1. Okay, we get about 4.3. And last one. ln of 160. Okay, 5.1. Okay, so the only point to me doing that is now I'm going to graph what's in blue. And I'm going to see, do these numbers in blue graph in a straight line? If they do, then I'm going to use a power model for this data. Okay? And then I can forget about the stuff in blue. Okay, I don't need it after I determine if it looks like a straight line, then the stuff in blue is done. I don't need it for the rest of the problem. Okay, now I'm going to graph everything in blue. Right, let's see how it looks. Okay, there's other ways to determine if you should use a power model, but I think graphing is the quickest, the easiest, simplest without getting into stuff that's too fancy. Let's make this nice and big. All right, so I'm going to graph 0, 1.6, best I can. Okay, 1.1, 3.4. So 1.1, 3.4. Right, I got 1.6, 4.3. 1.6, 4.3, and 2.1, 5.1. 2.1, 5.1. Okay, does it look like those points are in a pretty straight line?
Yeah.
Yeah. Okay, so all that means is go ahead and use a power model. Okay? If these points didn't look like they were in a straight line, I'd say, well, don't use a power model. Okay? Now we're done with what's in blue. That's all we needed it for. We don't need it again. Okay. Questions so far? All right. So, I think let's go to the calculator. Let's just do it that way. All right, since that's all we're going to be really doing from this point forward, I want to make sure everyone understands how to do it that way. All right, so if we're going to use the calculator, first thing we want to do is press Stat. We're going to go to Edit, and we're going to type in our data. Okay, so I'm going to press Stat. I'm going to go to Edit. I hit Enter, and then I can type in my data. Okay, if you already have data typed in, okay, and you need to clear it, you can just highlight the data and just press Delete. It'll get rid of what's in there. Okay, what I'm going to do is put all my X's, all the black values. Remember, we're done with these. Just cross these out so we don't get confused. I'm going to put all my X's in L1. I got 1, 3, 5, 8. Okay, then what I'm going to do is press my right arrow. I'm going to put all my Y's in L2. 5, 31.2, 73.1, and 160. Okay, so when you're done, that's what your calculator screen should look like. Any questions on typing in the data? Yeah.
So you press Stat or something?
Yeah, you press Stat and you go to Edit, and then you just type everything in. You don't have to use L1 and L2, but it does make it the simplest. So just I would use that.
How do you get rid of any extra number you don't need?
If you don't need one, you just highlight it, you just press Delete. And that's it. Yep.
Does it automatically use as like down there?
Does it use what?
The LN.
No, the LN, that was just for us by hand. We're done with that. So don't worry about those values in blue.
Okay.
We're done with those. The only reason I did those is to see, should I be doing what I'm doing right now? It was like a test. And it passed the test. It looked like they were a straight line, so you're good to go. All right, so now after we have all the data typed in, you're going to press Stat, go to Calc, and then the one we're looking for says Power Regression. So Stat, Calc, Power Regression. Okay, so Stat, Calc is the second one over on the top. Power regression, the fastest way to probably get to it is to press up, because it's at the very bottom of the list, so it'll loop around. And power regression on my calculator is choice A.
How do you hit choice A?
We're just going to hit Enter once we have it. Yeah. So Stat, Calc. If you want to go down, you can. It just takes a little longer. Eventually you'll get to it. Power regression. Okay, hit Enter. Now, as long as you put your X's in L1, your Y's in L2, nothing to change there. Okay, so just hit down until you get to calculate.
Mine did not do that.
Okay, you hit Enter.
Yeah, yeah.
Okay, so yeah.
It said power right on that.
Okay, yeah, so you're just going to be able to hit Enter. I'll hit Enter, and hopefully, did you get those numbers?
I got an error.
Get an error? All right, we'll have to check it out.
How did you get to that really off the bat?
So Stat, Calc, and then I go up to Power Regression. Okay, is anybody not able to get to this screen on the TI-84s? Yeah, if you have an 83, it's a little different. I'll have to come help you. Okay, and then go down to Calc, and it's going to tell you the two values. Remember I said we have to find the A and the M? Well, the calculator calls it different letters. Okay? They call it A times X to the B. We called it A times X to the M. All right, so this is how your book does it. Calculator uses different letters, but that's fine. All right, so now we just write down our final answer. All right, so we're going to fill in. What do you think we should really fill in for A? 1?
5.
5. Okay, fill in 5 for A. And for B? Well, what number do you think that really is? Remember, the calculator's rounding. 1 point what?
Oh, it's rounds, and what's around it to?
Well, it's estimating what it thinks the answer should be. But if you see a number repeat 5 times in a row, I would assume that number should probably just keep repeating. So really, B is what number? One and what? 1.6 repeating, or we could just say 1 and 2/3. Yeah. So really, B should probably be 1 and 2/3, or we could just write it as, how would you write that as an improper fraction? 5/3. Okay, so B really should just be 5/3, and A really should just be 5. Okay, so if you see a number repeat 4 to 5 times in a row, just assume that number keeps repeating forever, and then round it accordingly. All right. So let's write our answer. So we've got y equals, okay, fill in 5 for A. Okay, we leave the x. And then fill in 5/3 for B. And that's a power model for our data. Okay, I'll graph that in a second, and then I'll graph these points, and I'll show you it goes right through it perfectly. All right, so I don't think we're going to do it by hand. You just have to know how to do it on the calculator. All right, let me graph that. Okay, so we got y equals 5x raised to the 5/3. Now, if I want to graph it, what I have to do is turn one of my stat plots on. Okay, so I just went up to plot 1, hit enter, and turned it on. All right, if I use that as my window, will I see all these ordered pairs? No. What should I go to for an x max? Yeah, 10's probably fine. How about an x min? Yeah, 0 is probably fine. How about y min?
1, 0.
Yeah, anything around there is fine. 0 is probably good. And y max? Yeah, 180, 200, anywhere around there is fine. Okay, so now if I hit graph, there's my points. And there's the equation of the line we just found. And as you can see, it goes right through the points perfectly. All right, so what you could do now is they could ask you a question, predict what y will be when x is, I don't know, 4. You could just easily go to your table, type in 4 for x, and y would be about 50.4. Okay, so you can use that line to predict between the data points. Okay, that's called interpolating, okay, making a prediction. Hey, any questions on that process?
Yeah.
On that one, let's take a look. All right, so that's all that's really in the last half of section 5. All right, so our last section, chapter 5, we're going to finish up, is on 5.5, which is graphing log functions. Okay, everything you already know about graphing pretty much applies to these. Whether you're going to shift it, stretch it, flip it. If you know how to do that for all the other kinds of functions we've studied, same thing. All right. First thing I want to look at, though, is on the calculator, we only can type in logs with 2 different bases. When I press log, even though it doesn't write a little number down here, does anybody remember what base it's using? 10. So that's 1 the calculator can do. And how about ln?
E.
That's E. Those are the only 2 the calculator can do directly with buttons. So if I want you to do something like this, I want to know what's log base 6 of 5. Calculator doesn't have a base 6 button. Okay, so that's where we use this formula. Okay, change a base formula. And all you have to do to type it in is type the log of your argument and divided by the log of your base. And just use the regular log button, base 10. You can also do it as an ln. I would pick one of these two and just remember it that way. It comes out the same no matter which way you use. Right, so I'll type this in and show you how you do it. Okay, if I wanted to know what is log base 6 of 5, I would type in log 5, make sure I close my parenthesis, divided by log 6. Okay, and the answer is about 0.898. Or if I do it with ln's, ln 5 divided by ln 6, log of the argument divided by log of the base. Okay, remember, base, think bottom. Base is lower, so it goes in the bottom. You can't switch the 5 and the 6. If you do, it comes out wrong. Okay, but if I do it with ln, I get the same thing. Okay, so 0.898. And that's it. That's called the change of base formula. Any questions on how to type something in using the change of base formula? Yeah.
There is a button for logs with different bases.
Yeah, some calculators would have that. I know Kyle's wouldn't because it's older. But yeah, some calculators you can do it. I'm just trying to show a way that would work for everybody, no matter what. Yeah. Okay, even if you didn't have a graphing calculator, you could still do this, even on a calculator like that. Okay. All right, so now I told you that first problem we did, we're going to have an even faster way to do it. Well, that's the faster way. Okay. If we just took this and changed it to exponential form, we could have been done in one step. Okay, not that this was that bad, but 1.025, that would be my base. And, well, logarithms always equal the exponent. So t,
Oh, I should be 28 years or whatever.
and that's my answer. The reason I didn't write it this way, changing exponential form to log form, which we've done a lot, is because we didn't know how to type this in. Okay? We only know how to type in base 10 and base e. Now we know how to type that in. So I wouldn't have to go through all this. I would just type log of 2 divided by log of 1.025. That's exactly what we did. Okay? So we were using the change of base formula in this problem. I just kind of skirted around it, so I didn't really have to teach it to you at that point. Okay? But it's really exactly what we did in this problem. Okay. Does everyone see that? Changing log to exponential form to log form. Now you can type it in that way. Any question on that? Okay. Log of the argument divided by log of the base. That's exactly what we really did. All right. Now let's try something we can only do on the calculator, which is graphing calculator, which is graph that. Okay, John, do I have a button on a calculator to directly type in a base 3 log?
No.
Nope. So could you tell me how I could rewrite this so I could type it in?
Log x over log 3.
That's it. So let's type that in and let's graph it. Okay. Log x divided by log 3. Okay. If you have a stat plot turned on, I'm going to shut that off now because we don't need that anymore. All right, so log x, make sure you close the parenthesis, divide by log 3. Okay, also, if you adjusted your window for that last stats problem, let's do zoom 6. Okay, here's our graph. Let's just put that down there. All right, so domain. Let's look at how far left and right this graph goes. Okay, where does it look like this graph starts? Like the farthest left that it goes?
0.
0? Let's just see if we can actually use 0. Let's try it. Can we use 0? No. So it's everything greater than 0 up to infinity. It just keeps going. Okay, and here's where you can't really trust what the picture looks like. It almost looks like the graph stops on mine, it looks like about -2. Okay, on the y-axis. Let's zoom in. Does everyone agree on mine? It looks like it's about -2. Okay. So zoom in. Let's try to get pretty close to that spot. Does it look like it's going lower than -2 now? Yeah, here's -2 right here. That's -3, -4. How low does it look like it's going to go? Yeah, it just keeps going. But this graph is a little misleading. Okay, so what this should really look like is that. Okay, so this graph just keeps going down forever. What happens is when it starts to get very steep, the calculator has trouble sketching it. Okay, okay, so it's going to go down forever. How high is it going to go? It's going to go up forever, not very quick, but it's going to very, very slowly keep going up. So my range, -infinity to infinity. Okay, and that's the domain and range of every log function, unless you shift it. Okay, if you shift it left, shift it right, we can change the domain. Can't really do much to the range, though. If it goes up and down forever, it's always going to go up and down forever. Okay, if you take and shift this up 1, it's still going to go up and down forever. Okay? We can change the domain a little bit. All the transformations we already know apply to logs. Okay, so maybe real quick, we'll just write down what they are. Okay. What does adding or subtracting do inside your function? Which way does that stretch it or shift it? That's your horizontal shift. Yep. How about putting a number in front of x?
Horizontal stretch.
That's your horizontal stretch. All the horizontal stuff is always inside. Okay. How about multiplying by a number on the outside? I like the vertical, but it's not a shift. It's a stretch. And D?
Vertical shift.
That's your vertical shift. Okay, as always, the horizontal stuff is backwards. Okay. If I put in a plus, which way is that really going to shift it? Left. And if I do a minus, that's going to shift it to the right. Okay. If I put in a big number for a horizontal stretch, big numbers make it smaller. They compress it. Small numbers make it bigger. Okay? A small number would be something like 1/2, 1/3. That would actually make it bigger. Vertical stuff, everything is what you see is what you do. A bigger number would stretch it bigger. A smaller number would compress it smaller. A positive number would shift up. A negative would shift down. And what would happen if b was negative? That's a flip. Okay? That's a horizontal flip, so it flips over the y-axis. What about if c is negative? It's a what?
On the vertical side.
What's going to happen vertically?
Flip.
It's going to flip. Okay, so a vertical flip looks like this. If you had that picture, now you get that picture. So that flips over the x-axis. That's a vertical flip. Okay, so our first question says, basically, I'm putting a negative in front of x. Okay, just asked you what that did. So first thing I want to know is what I would have to do to the original to get that. Okay, so I just want the transformations. In this case, it's just one transformation.
Horizontal flip.
Yep, it's gonna reflect. You could say reflect horizontally, or which axis is that over? The y-axis. So it's gonna go like that.
So flip over the y-axis.
Yep. So I'll say to graph y equals log base 3 negative x. Flip log base 3 of x over the y-axis. That's it. That's the only transformation in that problem. And now they want to know the domain, range, and vertical asymptotes. Well, if you remember what the domain and range was before, okay, basically your graph now is flipped. It's going the other way. So what would my domain be?
B0 to negative infinity.
Yep. So just imagine it going that way. So it's negative infinity up to 0. Do we include 0? No. You can't take the log of 0. That's undefined. Okay. And the range? What's the range going to be?
Positive to negative to positive.
Negative to positive, what, 2? 3?
Infinity.
Infinity, yeah, infinity. It's still going to go up and down forever. Okay? Even though it looks like it's leveling off, it still goes up very, very, very slowly. Okay, and did our vertical asymptote move? No.
No.
Okay.
Horizontal one did.
There's a vertical, again, the calculator doesn't show it very well, but there's a vertical asymptote right on the y-axis. It will never touch that. Okay? It'll get close, but it won't touch it. Okay? So vertical asymptote is still x equals 0. Okay, and there are no horizontal asymptotes here because it's going to go up forever. It's not like it's going to level off and stop. It just keeps going up. Okay, any question on that? All right. All right, another transformation question. What might we want to do first here? This isn't, it's not written the way we normally write it.
Negative as positive. That's the final answer. Negative as positive.
Yeah, I would rewrite it as negative x plus 3. Okay, that's how we normally do it. Okay, and we'll just write our transformations. Okay, how many transformations here? 2. And you do them in the order I have the letters. Okay, that's why I used A, B, C, D. All right, so let's start with the plus 3. Jamie, what's the plus 3 going to do?
Horizontal shift left 3.
Yep, so we can just write shift left 3. Just say the direction and say how much. Horizontal shift is that's fine to say too. Okay. And the negative x. Matt, you remember from the last problem what that negative x does?
Flip over the y.
Nice. Flip over y-axis. That's it. That's all there is for that one. Any questions on that? What if I put a plus 2 outside the parentheses at the end? What would a plus 2 do? Which way?
On the right.
Up or down?
Yep, it's up or
It
down.
depends on the sign.
If it was a plus, say plus 2,
We'll shift it up.
we would shift it up 2. Yep. What if I put a 4 in front? What would that do? Yep,
Stretch.
stretch by
Vertical.
vertical. By how much?
4.
Yeah, I would say vertical stretch by a factor of 4. Okay. So any questions on what those numbers do? Okay, we've done them so much, I'm not going to go through one of every type. All right, so in general, when we want to sketch our log functions, if we can find where it crosses the axes and find the vertical asymptote, that's pretty much all we need. Sometimes we don't have a y-intercept. For example, if you had a log function that looked like this, that graph's never going to cross the y-axis. Okay, it's just not. It'll always cross the x-axis, because log functions go up and down forever. So if you go up and down forever, at some point, you're going to cross 0. Okay, but not always a y-intercept. Right, so to find your vertical asymptote, it's normally on the y-axis. Okay? But it can shift. It can move left and right. Just set your argument equal to 0 okay, and solve it. And that's how you find your vertical asymptote. Okay, set your argument equal to 0 and solve. Okay, if you don't remember how you find x and y intercepts, that's just a reminder. Your x-intercept is when you fill 0 for y. Your y-intercept is when you fill 0 in for x. That's it. That's all there really is to graphing it. Okay, if you need more points, you can use your calculator, use your table. If you feel like, you know what, I need to figure out what the curve looks like a little bit more, use your calculator. Okay, but remember, when you plug stuff into your calculator, the log function only goes one direction. Don't try plugging in -4. Okay, if you try, that's not going to it's not going to be very helpful. Okay, you got to plug in numbers that actually give you answers. Okay. Okay, so that's what this part means. Just make sure you're plugging in numbers in the right direction. Okay, if you don't, it's not a big deal. You're just going to see the word error. Keep trying until you don't get error. All right, let's try sketching that. Okay, log base 2 of 3x plus 5. Okay, first thing I'm going to do is I'm going to set my argument equal to 0 and then find my vertical asymptote. Okay, so Tyler, what's my argument here? What's the thing we're plugging into the log function? So in this problem, the argument is the thing that's plugged into the log function. So like if I was going to type this in on a calculator, what am I taking the log of? I know the base is 2, but it's log base 2 of 3x plus 5. Okay, this is my argument. Okay, the argument is the thing that you're taking the log of, or the thing you're taking the square root of, or whatever it's the function is. Okay, so we take that argument and set it equal to 0. So Paige, how do I solve for x?
Subtract 5.
Yep.
Divide by 3.
Subtract 5 divided by 3. There's my vertical asymptote. x equals negative 5/3. All right, let's put that in. Okay, if you're not sure what negative 5/3 is, that's negative 1.6 repeating. Okay, so put a vertical asymptote at about negative 1.6. All right, next thing I'm going to do is I'm going to try to find my intercepts, but I'm going to use the calculator to help me out. Okay, so just type this in, and we're going to use the table. So remember, type it in as log of your argument, divide by log of the base. So log, let's make it 3x plus 5. Okay, and what's the base? 2. Base 2. Okay, go second. Go to table. Okay, I'm going to start with my my y-intercept. Okay, so when x is 0, I'm at about 2.3. So on my graph, put 0, 2.3. Okay, I can go as far out as 10, so that's just because of my graph paper. So I'll try a point at 10. And I get 10, 5.1. Okay, now is this curve ever going to hit the green line? Nope,
No.
that's an asymptote. So basically it's just going to come up. Looks something like that. Hey, if you want to get another point in here, you can, but that, to me, that's accurate enough. So we just use those points. Okay, and let's see how it looks compared to the calculator. All right, now mine doesn't look like that. What's going on in this picture?
Too steep.
Yeah, it's too steep. All right, so it looks like it's, if you zoom in, it looks like it's stopping maybe about just after -1. If you zoom in, you'll see that going down more. Okay, so if you sketched it like that on the test, I'd mark that wrong. Okay, it does go straight, almost straight down. Okay. So any questions on that? Right, I think that's the only sketch we'll do. All right, so last thing we'll look at with a log is a formula we can use it in. Has anybody ever heard of this Richter scale before?
That's what they're called.
Yeah, it measures how strong an earthquake is. Yeah. So that's one use for a logarithm. Okay, and usually when you hear earthquakes, you hear a number like, it was a magnitude 4.7 or 5.6, something like that. Okay, but so here's the numbers on your earthquake scale. And they go, I think the highest magnitude may be up around a 9 point something. I don't think they've ever had a 10. That's when the planet cracks in half. But if we take a look, the difference between a magnitude 1 and a magnitude 2, you might say, oh, it's just up one number. Well, that's 10 times as powerful when you go from a magnitude 1 to a magnitude 2. And then when you go to a magnitude 2 to a magnitude 3, it's the same thing. It's 10 times as powerful again. So if you went from a magnitude 1 to a magnitude 3 earthquake, what's the difference? It's 100 times more powerful. Or a magnitude 4 is 1,000 times more powerful than a 1. Okay, so people think, it's just a difference. 1 to 4, it's 3 apart. But it's a factor of 10 each time because it's a logarithmic scale. Okay, so now if you compare like a magnitude 2 to a magnitude 6, there's no comparison, right? It's many, many times more powerful. Okay, so R, that's the number you see on the news, magnitude 5.6. Okay, that's what they simplify it to. A is something they'll give you in the problem. It's called the amplitude of the vertical ground motion. So how much the ground is moving, measured in micrometers. Okay, T is the period of the wave. Okay, earthquakes are basically a wave. If you think about like throwing a big rock in the middle of a pond, you get that wave rippling out. Think of that as like an earthquake rippling through the water. Well, the same thing happens on land. Okay? The land actually can have a wave go right through it. Not a huge problem if there's not buildings on it and cars and people, but if there's structures on that land, that wave can cause the buildings to fall apart or sway, things like that. And B, that's a factor that accounts for the weakening of the wave. Okay? Same idea as a pond. Think of dropping a rock in the middle. By the time that wave hits the shore, it's a lot weaker than it was right at the center.
So what should we write for B? It's just
B is just a factor that accounts for the weakening of the wave. And it seems complicated, but they're gonna give us everything here, so it's not that bad at all. Okay. And in our problem, it says at the early stage of an earthquake, okay, the vertical ground motion was A. At a later stage, it was 10A. Okay, it became 10 times as much, 10 times more powerful. What's going to be the change in intensity? Now, if you understand what I explained earlier, you might already have an idea if something is 10 times more powerful. What's the difference on the Richter scale? How much? 1. Yeah, it's a magnitude of 1 different. So the answer we get here should come out to 1. Okay, let's see if that's what happens. We're going to assume everything else stays constant throughout the whole problem. Okay? We're going to assume that the weakening of the wave, that stays the same. We're going to assume the period of the wave stays the same. In reality, this could all be changing. It would be more complex. But we're just going to assume it stays the same. Okay. Key here is change. If you want to find a change between two things, say like your grade on the last test, your grade on this test, you want the difference, the change. What do you do with the two numbers?
add them up and divide by 2.
Right, if you wanted an average, you would. But if I just said, or even like the temperature this morning was 23, the temperature now is 31, what's the change? What do I do?
You just subtract.
Yeah, just subtract them. Usually we subtract the more recent, okay? Or we'll say at a later time minus the earlier time, okay? Like earlier today it was 20, later today it's 30. We do 30 minus 20, tells us it went up 10 degrees in temperature, right? So we'll find intensity, we'll call it at a later stage, minus intensity, we'll call it early stage. Hey, and we have a formula for the intensity. Just fill in. That's the formula for the intensity. So we have log, in parentheses. It says, now I need the amplitude of the vertical ground motion. Okay, what was the vertical ground motion at the early stage? It's not a number, but they do tell it to us. Yeah?
It's just A.
Yeah. At the early stage of an earthquake, the vertical ground motion was A. Okay? And all the other stuff we don't know. So just leave it. Okay? Period, we'll just call it T. The factor that accounts for the weakening of the wave, we'll just call it B. There's only going to be one difference between what we put here and what we put here. Okay? One thing is going to change. What's the only letter here that changes at a later stage? Yeah, A becomes how much? 10A. That's the only difference. Period of the wave stays the same. Weakening of the wave stays the same. Right. And I put that in parentheses because you're subtracting this entire thing, which means what do you really do with this negative? Yeah. Both parts are subtracted. Okay. Watch what happens when you do that. The first part just stays the same. Okay. The second part is going to become minus log 10a over t, and then minus b. Okay. What's going to happen on this line? Yeah, what cancels out? The b's. Plus b, minus b. So in other words, the weakening of the wave doesn't matter because it was the same before, it's the same now. It didn't change. So it didn't make a difference in our final answer. So now the b is gone. Okay. Next thing I want to do, we're going to get another letter to cancel out. And to do that, I'm going to split this up. Okay, when we have division, how does that split into two logs? Is it a plus or a minus? That's a minus. Log of the top minus log of the bottom. Okay, that's what we did on the last test. Whenever you have a fraction, take the log of the top minus the log of the bottom. Okay, and I can do the same thing in this part. Okay, I'm about to subtract this entire quantity. Okay, so I'm going to split it up. What's my first argument going to be? 10a, plus or minus? Minus log t. And now what do we do with this minus in front again? Distribute. And now watch what's going to happen again here. Get log a minus log t minus log 10a. And what's minus log t? Plus what? Plus log t. Okay, look very carefully at that line. What's going to happen here? Plus log t minus log t. So in other words, the period, or t, the period of the wave, doesn't make a difference. It was the same before, it's the same now. It has no effect on the final answer. The only thing that was different was the a and the 10a. So the last thing I'm going to do is put these back together into a single log. Right now they're subtracted. How does subtraction recombine? Multiplication or division? What is it?
Division.
Yeah, it's going to recombine as division. Okay, and we would have log, let's see. Okay, what would go on top? Yeah, you know what, actually, I think what we should have done is probably switch the order we subtracted in. So what I'm going to do is just switch it right at the very last step. And I'll show you what happens. So what should go on top now? 10a. And what would go on bottom? A. And then the a's would cancel out. And the only thing you're left with is the log of 10. When I type that in, what do you think I'm going to get for an answer? Yeah, the log of 10 comes out to 1. So a difference in 10 times the amplitude, it's a difference of 1 on the Richter scale. Okay, the only reason I had to flip it is because I think at the very first step, we probably should have switched the order we subtracted in, but all the same stuff would have happened. Any questions on that? All right, so the Richter problem in the homework tonight, it's a lot easier. They're going to give you A, T, and B, and all you have to do is plug them in and get an answer. Okay, so it won't be as hard as that one. All right, so from the first part, 5.4, okay, on 293. Okay, try 35, 36, 43, 46, and 48. Okay, 48 we actually did in class. That was a power model. That's the second one I went over with you. So if you wrote that in your notes, you already got that one. Page 301, it says 1, 5, 8 through 10, 16, 23, 25, 28, 42, and 52. Okay, we'll take a look at that tomorrow, and then tomorrow we'll start chapter 6.